Good morning everyone, I'm Strish. Thank you for joining me. For this video, we are very quickly talking about this concept why alkynes are reactive. These are those hydrocarbons with the triple bond functionality, carbon, triple bond, carbon. You know it to be something which looks like this. Here's your alkyne functionality. These type of compounds are reactive. The basic essence of it is that they are very high energy compounds. If we can answer why they are high energy compounds, we can also answer why they are reactive. Look here at the dissociation energy, the energy which is required or given off upon breaking of a bond. If you look here at acetylene C2H2, the dissociation energy per mole is 229 kilocalories. When you look here at ethene C2H4, we have 173 kilocalories per mole. When you look at ethane CH3 or C2H6, it's 90. A considerable drop in dissociation energies as you're going from triple bond to double bond to single bond, and you have to keep this in the back of your mind. Alkynes have high dissociation energies. A lot of energy is given off when you break off that bond because a lot of energy is stored in that bond. Now let's look at material directly relevant to our question, why are alkynes reactive? We will answer that question using this model compound C2H2, acetylene or ethine. You can ignore points 1, 2 and 3 for now. If you look at everything in terms of hybridization and orbitals, this is what you have. You have a carbon, there's a hydrogen over here and a hydrogen here. The carbon and the hydrogen are sharing one electron each, and you know this would generate a single bond between the two. You would have a sharing of the electrons in terms of orbitals, as you can see. These will form what are sigma bonds, and the orbitals which are involved here are sp orbitals, meaning there's a character of both s and the p orbital coming together and developing in hybridized form, and that hybridized orbital, sp orbital, will form the sigma bonds. These are not directly relevant to the reactivity of alkynes because we're focusing here on the triple bond functionality, but it's a start. When you look here between the carbon and carbon, there's an electron being shared, and again sp orbitals are coming together to form what is another sigma bond. When you look here at C2H2, you have 3 sigma bonds already in the formation, and they all involve sp orbitals. Now let's look at our pi bonds. You have in the vertical plane a p orbital, as you can see, but in the p orbital for each carbon there's an electron, and the interaction of these will generate a pi bond. That's what it is. Now in the plane which is perpendicular to this plane you're seeing for the pi bond, you can generate another p orbital, and it would look something like this, one behind and one in front. These are like donut shaped rings. You can put an electron here and an electron here, and then we can generate another pi bond. So now when we're looking at C2H2, what do we see? In its entirety you have 3 sigma bonds and you have 2 pi bonds, but in terms of relevance you're only looking at this sigma bond and not the sides, so we'll change the 3 to a 1 because this functionality will always involve 1 sigma bond and 2 pi bonds. As you can see, between the carbons you have 1 sigma bond and 2 pi bonds. Now keep in mind the following points. When you are looking at these 2 electrons here, if I want to, just for the purpose of this video, bring them together right over here, here's one and here's one right here, and these 2 electrons in the other set of p orbitals, bring them right here in the middle and right here in the middle. Now I have all my 6 electrons here in a single line. 2 of those electrons forming the sigma bond and 4 forming the 2 pi bonds of this functional group. Now focus here on point 1. You have a concentration of 4 pi electrons in a small volume of space. Your 4 electrons are in these, 2 from one and 2 from the other. That's 4 pi electrons in a small region of space. Point number 2, these electrons, your pi electrons, 4 of those are going to have electron to electron or pair to pair repulsion. Electron pair repulsion will occur. We're not looking here at the sigma bond electrons, we're looking here only at the pi electrons. If you were to look at everything in terms of the carbon, you could say you have a cylindrical region of space in which you're looking at 4 electrons always present. In that region of space you have significant electron to electron pair repulsion. Point number 3, when you compare the sigma bond to the pi bonds are weak because of the effect of the previous 2 points. The repulsion, the concentration leads to a significantly weaker pi bond versus a sigma bond, which is why then the pi bonds want to react in terms of reactions, break away and generate sigma bonds. If you think about many of the reactions which involve alkyne functionalities, they will go on to generate single bonds or double bonds, where you are seeing a larger proportion of sigma character than pi character. In the alkyne, you have a higher proportion of pi character to sigma character, but after the reaction, you'll have a higher character of a sigma bond or sigma characteristic versus a pi. And that right there is a good point to remember. When you have alkyne reactions, you're going from compounds which have a high pi character to compounds which have a high sigma character. Because these bonds are reactive, they break away and they generate sigma bonds. If someone were to ask you why are alkynes reactive, these are your points. 4 pi electrons in a small region of space, significant electron to electron repulsion, and the bonds in itself, the pi bonds, are inherently weak. And that right there is the end of this video. Thank you.